Hi, I'm Robert Burke. I am a senior SWE at Google who's lately been working on the Apache Beam Go SDK. Earlier this year I was made a Beam committer, which makes things much more convenient for me to... And yeah, you can find me as @LostLuck on both Twitter and GitHub, and as my Apache alias as well. I've been working on the Go SDK since around late 2017 or so, and at the moment I believe I'm still currently the foremost expert on the SDK, so this is why I'm here. So hopefully to get more experts in the pipeline. So this is what we're talking about, the Go programming language as an SDK for Apache Beam. A little bit about it. It is actually, despite Python's vast, bigger usage, the Go SDK is actually the first purely portable SDK. There's no legacy version of the Go SDK. So there's only one way to run portable or pipelines in the Go SDK, and that is using portable runners and frameworks. Currently, we run the test suite for the Go SDK on all of Dataflow, Spark, and Flink, which is pretty darn nice. It's all in batch mode right now. It was originally developed to cover a large series of batch use cases inside of Google, and this is where the perspective I have comes in, because I am mostly making it so that the batch use cases work very well. And as a little bit of kind of a carrot for paying attention to this talk, I hope you kind of get an idea of how SDKs end up needing to work. So possibly we could get other SDKs going, like, I don't know, these other fine languages with cute mascots or logos. So that begs the question then, what is a Beam SDK really doing under the hood? From my experience just working on the Go SDK, it felt like there's really two categories of things that need to be done, and that is construction and execution. You need to be able to specify your pipelines in the language of your choice, and then also be able to execute them when the runner hands the bundles back to you. And you'll be seeing a lot of these cute little gophers throughout this talk, because that's just how Go rolls. But the other part of what SDKs need to do is that both also need to kind of mesh well with the language that they're written in. But as well as also match all the model stuff for the Beam. For the Beam model. It's been a wonderful week already. Which is why I kind of like the duck-rabbit picture here for that. This talk is not going to be trying to sell you on Go or the Go SDK in specific. If you want to learn more about Go specifically, there's a wide range of resources. There's the Go Tour, which I hardly recommend if you want to learn how the basics of Go works. There's more in-depth knowledge on the Go Wiki. And of course, my favorite, the Go Playground, where you can just go to the website and try the language. And with that in mind, let's just quickly tab over to a quick demo I have. So one thing the Go Playground got fairly recently was the ability to just sideload any arbitrary package available on GitHub. So if you know the import path, you can download it and then try it out using the Go Playground. So I decided to try this with the Go Direct Runner. So I'm going to demonstrate a quick little Go pipeline for you right now. Since it takes a moment... Oh, that actually ran significantly faster than I expected. Yeah, so this is just a quick little word count. It counts the words in, and sums the words in modern major general. Just does so in memory with a beam.create statement. Goes ahead, splits up all the lines into individual words, use the stats composites to count the words, and then because this is just purely in memory, just prints everything back out. And you can see it processing the pipeline, figuring out how everything needs to go together, and then just outputting all the words. So, is this the first time anyone, yeah. Is this anyone's first time seeing a Go SDK pipeline in action? Ah, welcome. Now at this point, I am behooved to ask, who here actually programs in Go? Raise your hand. Okay. Who needs a quick little crash course so that the code is easier for you to read? Because there's a little bit of code. Okay, that's totally fine. Just going to open a clean instance of the Go playground. So, very straightforward. This just quickly runs a simple hello world function. So, variables, we'll start with those. The main thing that is different between many languages most people are familiar with and Go is that the types are actually the suffix. They're the second part of the declaration. So you can declare a variable like so. My cool string is a string. But of course, no one really just declares a string, especially when it's in a demo like this. You can also just declare them as implicitly just by writing the string itself. So my other string. This is a good string with typos. Other fun little things about Go. It doesn't like it when you use strings and then, or you write variables and don't use them. That is not really pertinent to reading any of the code. It's just a fun feature I enjoy. My other string. You can kind of see the syntax for functions with the main function there, where it is prefixed with func, and then whatever the name is, and then whatever the argument types are. Again, the name of the variable is first, and then the types, any number of types, and then you can return almost an arbitrary number of return values if you like. This is a poorly named function, of course, because this is just all ad hoc, whatever I'm thinking of. And let's just format things so it's a little cleaner to read. Undefined my cool string because I didn't quite do the camel casing. Voila. So you can write your functions like so. You can define variables like that. And the only other part that you really need to grok the rest of the code is defining types. So I'm going to show you a simple struct type. Structs in Go are pretty straightforward. You define the field name and the type itself. And then you can just declare things as normal. So one last thing here. And let's actually go with printf. Ta-da! Very straightforward Go code, and the URL there again is to get to the playground is just play.golang.org for your own experimental needs. Right. So, like I said, this is a guided walkthrough of the Go SDK, and personally I play a lot of video games, and you wouldn't have a very good walkthrough without a map. So I've constructed a very light world map for you that we're going to explore throughout this talk. Of course, we haven't seen the whole thing yet, so it's a little shrouded in mystery. But as we explore, our little gopher hero here will be very well equipped to face the challenges of doing all our data processing down the road. So our first stop is the Beam package, where most of the user code resides. So anything that is facing the user is in the github/apache/beam/sdk/go/package Beam. It's a little wordy, but namespacing being what it is, that's just how we get the package. For brevity, I'm largely going to go with the shorter names after that long prefix. So here's what the Beam package contains. And it mostly contains all the parts of the model that you are very familiar with if you're already familiar with Beam. So constructing your pipelines, getting your P collections, defining coders, P transforms and all their various kinds, side inputs, windowing, so on, and all the little features of Beam that you kind of know and love. With the exception of state and timers, because those aren't yet implemented in the Go SDK. I have a long list of what's not implemented later in this talk. For the actual how things look, you saw a little bit of this already with the demo I gave, but generally you'll see these two parts here, the inits and the new pipeline once per pipeline, and everything else is kind of self-explanatory. For running your DoFns, we have pardo. For grouping things, we have CoGroupByKey. For doing more advanced combine operations, we have combine and combine per key, flatten, so on and so forth. For P collections, P collection types in the Go SDK are implicit, unlike which is very close to what's happening with the Python SDKs. Sadly, Go does not have generics, so our P collections can't be generically typed. This leads to some other problems down the road, which I'll get to in a moment. But the Go SDK by itself supports any arbitrary user type that can be constructed from the main, like the main primitives. They can be retyped versions of the primitives themselves for better type check safety. Structs that contain multiple fields, so on and so forth, including like arbitrarily complicated structs with multiple levels of definition. Depends entirely on what you actually need in your pipeline. What does a pardo look like? I skimmed over it very quickly in the demo, but any arbitrary Go function has the potential of being your DoFn. In Go, there is no inheritance. Things are built largely based on composition. So we end up doing some type inference in order to construct the pipeline. In this case, this bar counts function takes in a value of type foo and returns a kv pair of string and int. You'll note that the phrase kv doesn't appear anywhere on the slide here. Again, without generics, we have to do things a little differently. So in this case, the Go SDK was designed with implicit KVs. So when you return two values from a function, they're going to be the key and the value respectively. Then you simply just pass things in to the pardo function along with the P collection as input. But it doesn't even have to be your own function. You can use any function that kind of satisfies what you need to write down. So for example, the strings package in the Go standard library has a title function. It turns strings into strings. That is perfectly valid to use as a pardo in your pipeline. Just relying on functions would not be very sophisticated because we only have access to basically the process element function. Instead, you can actually have structural DoFns, which have better, deeper access to the bundle lifecycle. In this case, I'm showing off just the process element method, but you can have other methods as well for invoking things at the beginning of bundles, at the end of bundles, or even one-time setups. Again, all the types are inferred and from the signature of the process element function. So in this case, we are taking in a foo, and then we're emitting any number of strings or ints as KVs. aside from the slight difference in how we're defining a struct value here, we're just passing in a single instance of the structural DoFn, and Beam will take it from there. This is the approximate full possibility of what you can put as your process element or part of your function signature. You'll note that there's a lot of optional types here, but you can pass in the Go context, you can pass in the event time, and windows, the actual main input, side inputs, different emitters. Again, if you want to change the event time, you can return it out, get the standard output, and then optionally, of course, because this is Go, error. Input or output are either the single or pair of KV types. And all of this is kind of implicitly derived. When you have any of these as part of your signature, the framework at execution time will pass in the correct value into that slot, and you can use it as normal, just if it was any other normal Go function. Or side inputs. So this is where there's kind of a hilarious question of, we don't have generics in Go, but we do have first-class functions. So you'll note that I kind of glossed over how emitters worked, where we were just spitting out ints or strings or pairs of strings and values, and those are just being passed around properly. We take advantage of first-class functions because we don't have generics. So with that, we get a little bit more type safety within the user do functions. So during testing and such, you can be very certain that everything is working properly and that the compiler is on your side, at least for your code there. This slide is showing off the different varieties of side inputs. Side inputs are also kind of functional parameters as well. The main one at the top here is the most general one, where it is an iterator function. It takes in a pointer of whatever type you're iterating over and returns a Boolean if the value is any good. So you just simply define it, start iterating it over in a for loop, which you'll note that this just satisfies this is something I didn't demonstrate earlier, but for loops, you'll note that there's a lot less parentheses compared to Java. You'll also note that there's no semicolons. I should have led with that as well. But we can iterate through the various values there. We do have some additional convenience functions so that for side inputs, so that you can just get things as a slice of values, or just as a singleton value if you know that your P collection only has one element in it. And you can specify side inputs to any of your DoFns using the additional side input option here and passing in the associated P collection so everything gets wired up properly. CoGroupByKey, also very similar, takes in takes in any number of iterator functions that match the values. This is where I have the lovely diagram kind of hopefully making a little clearer what CoGroupByKey does. But it takes in any number of KV pairs, or P collections of KVs, that all have matching key types, and then produces a CoGroupByKey type that leads with the key, and then has any number of value of the same number of value iterators on the side afterwards. And your DoFn here that processes the KVs gets all the values associated with that key. And you specify that by getting you just run a CoGroupByKey and then have the appropriate pardo afterwards. Combines, again, combined funds are a fundamental part of the Beam model. They can start off as simple as a regular binary merge. In this case, we're just summing all the values together. But you can have more elaborate combined funds as well, where you break things down into the liftable steps of add input, merge accumulators, and extract output. Finally, this is kind of a nice, concise view of an entire Beam Go pipeline. I've omitted how stats and any other composites work, but they functionally use all the same primitives you've just seen in order to construct additional parts of your pipeline. and to perform the operations that you want. So with that, we've left the land of the user pipeline and what most end users for the Go SDK will end up using. So now we need to answer the question of how the heck do we actually get it to work? Because right now we've specified what we want and what parts we want, but not how we're actually going to execute it. Part of the core of that is you might have noticed that while we have all these things that have specialized names and such, we don't have any inheritance, we don't have any overloads in Go, so we can't really, we don't have those particular powers to just extract the methods out. So inside the package, off in Beam core GraphFun, we have a function called graph.newFun that we use internally. And what it does is it basically analyzes whatever you're passing in as a DoFn and figures out its particular type signature, what P collection it needs, and what methods it actually satisfies. And then additionally, another step checks to make sure that all the types are appropriately consistent. And these allow for the different kinds of both just regular functions, which will behave as either the process element method or the merge accumulators method for combine funds, or whether they are structural DoFn that has all the various lifecycle functions. This is done using Go's fairly robust reflect package. While you're going through the SDK, you might also notice that there's a whole bunch of X packages. Partly this is because what we're operating on happen to be a lot of keywords, type, func, so just suffixing X gets around that particular nit. But also kind of they largely, the X packages are largely for helping out, for their tools that operate on those particular types of things. So if we're working in the SDK. So the typex package helps you work with types. The funcx package helps you work with funcs on an abstract level, so on and so forth. This brings us down to, once we have our functions, we also need our P collection types to match everything up. We use something called the full type class or interface to transport the types implicitly at pipeline construction time. And it maintains kind of what kind of type it is. In this case, the class kind of returns whether it's a CoGroupByKey or a KV, so on and so forth. The type is actually, oh, no, I messed that one up. Type has whether it's a CoGroupByKey or one of the concrete primitive types or one of your own user types. The class is a little abstract in that it is representing whether it is containing containers of things and so forth. And then components actually does the recursive trace down. So for KV type, it would contain the two primitive types. If it's the CoGroupByKey, it would contain the key and all the different value types. And these are largely used so that we can type check your pipelines. Since we don't have generics, we can't have the Go compiler do this for us like it's being done for Java. So instead we take a leaf out of the Python book and just do it at runtime. Since Go has very robust static type checking by itself, and that information is available to the reflect package, we make sure that as much as possible that your pipeline is sound in terms of what types are getting passed around where, so you don't get an esoteric runtime error at execution time when you're actually trying to process your data. That would be no good if you're several hundred steps in a multi-day long pipeline and suddenly something breaks. So getting those errors out of the way first is very valuable. So for an example, if you've got a P collection that contains ints, and you try and pass it to a Pardue that takes in strings, it will fail. But if you're taking that same P collection of ints and passing it to a function that takes ints, that's also good. Same thing for if it's a structural DoFn. As far as the system is concerned, these two are the same. They're both DoFns that take in p collections of ints. That's sorted out. We kind of know how we've got all our types. We know our DoFns, so forth. How the heck are we going to cross the river of portability? On the other side, we want to actually be able to like pass it's like have the runner manipulate things, but we also need to be able to have it so that any of our arbitrary worker machines can recreate our work and produce working segments of pipeline to pass the data through. So if you've been paying attention to the other talks on portability, you might have heard of the Beam runner proto and the actual pipeline proto. What this actually contains is basically a list of all your P transforms, a list of all your P collections and all the coders, some other things as well, but it mostly connects them all together with global string identifiers per type, as it turns out. And most importantly, especially in terms of P collections, or P coders and P transforms, the actual types and coders and DoFns, something that represents them so we can get them out afterwards. I'm bringing this up because the next part of the talk is serialization, and not actually for your data, but for your types and P collections. And you're probably rolling your eyes at me if you are familiar with Java or Python, because those languages provide fairly robust, ingrained mechanisms to serialize your various classes or pickle your various types, even just at the language level. Go does not provide this mechanism, so we've had to work around it. So what we actually end up doing, if in absence of anything else, if you have your types, we use the reflect package to synthetically serialize your type. So if it's a struct, we say it's a struct. We say it has these fields with these names and these types, so on and so forth recursively, all the way down. And then on the other side of the divide, we would synthetically reconstruct this type. And it turns out that if you've done all of that correctly, you can just cast that into an actual instance of the type and it will work, because it's got the same memory layout. Similarly for functions, there's no arbitrary symbol that we can just use to get access to that function in Go. Go does not provide this, partly because it allows for better pruning on the compiler side. If you're never using the function, there's no way to expect it or access it. Since you are referring to it in your pipeline, though, we know that it is in the debug symbol table. So that is what we do on the worker side if nothing else has been done. We literally save the pointer and the name, and then we look it up in the debug symbol table, and then use some unsafe mechanisms to cast it to the expected function signature. And that also works. You might notice that I really don't like talking about this because it's terrible. I do not recommend any of this for production usage, but it's very convenient for just trying things out. Instead, what we recommend for production usage is to actually just register your functions and your structure, whether they're your functions, whether they're just vanilla functions, and your structural DoFns, and all the different types that you're passing around, because then we can just use those names very directly as the representation of those types instead of their synthetic constructions of those types, because then because then we have access to them on the worker side. And this avoids all that nonsense with synthetic construction and debug symbol table lookups. At this point, we basically we have strings, we have payloads, we have all the listings of what your pipeline's actually doing, and we just toss it into the river to the runner and say goodbye for a while. I'm not going to talk about what runners do. There's a lot of talks on that already. On the other side of the river, we have to actually do things on the worker side. That's actually a good label, I should add. But besides the point. At construction, on the worker, the first thing that needs to start up is the actual SDK harness, so that it can start receiving things and understand how that works. The worker harness on the SDK side basically follows these steps. It connects to the runner side of the worker via streaming gRPC, starts asking for instructions, and then it starts executing the instructions. And it just does that until it's killed. In Go, this kind of looks like this. The different kinds of instructions that a worker can get from the Fun API side of a runner are pretty straightforward. It's register whatever bundle processor and what p-transforms are being operated on, something to actually process the data, something in order to report back the progress on each bundle, and whether the bundles should split or not, which is a lovely little optimization I'm not going to get into. And with that, we have our actual toolkit. We still need to actually execute things, though. Pardon me. It's probably, you'll have to forgive the untidiness of these diagrams. When I first gave this talk, my laptop had broke, and I had to finger paint these on my phone. So you'll have to excuse that for now, and then I've just been busy since June, so I have not had time to redraw these with a little bit more fidelity. On the worker side, this is where Beam Init comes in. Beam Init is actually not just for saying, I'm about to construct my pipeline. It serves a better purpose on the worker side, where it is basically setting the divide between this is what is happening at the original controller process versus this is what is happening on the worker. Anything after beam.init in the construction process on the worker is never executed. We don't reconstruct your pipeline. So before beam init, everything is executed everywhere. After beam init, it's only called in the main program. I mention this because that means if you have anything that you want to actually do on every single worker, you would just put it before beam init, and then every single worker will call it, right before it starts talking to any of the runner side stuff. That's particularly important for all the serialization mechanisms I was mentioning earlier. Did I have a slide on that? No. So yes, so anything that's called before beam init, including any of the packageable initialization stuff, that makes sure that all the code that we're setting and all the maps that we're configuring for all those registrations I talked about are available to the worker so that everything can happen efficiently. Afterwards, once we get these various process bundle requests, we essentially have a large type switch in exec/translate.go that goes through and turns the URNs and the payloads into the actual code that you wrote and hooks it all together. These executable units basically pay attention to the bundle lifecycle because that's all they know. You're going to start a bundle, process all the elements, and then finish the bundle. While we're passing things down between these p-transforms, the Go SDK, again, doesn't have generics, so all of this is implicitly typed. We have something we call just the full value wrapper. It contains either the K or the implicit KV, the associated timestamp in the window, basically all the windows. So basically all the information that is is part of the Beam model so that more advanced transforms can be handled. In order to handle streams of data, we have two different kinds of interfaces, which you did not see at construction time, but these values are basically how we handle abstracting out any of the CoGroupByKey streams or any of the side input streams. Very simple interfaces to manage that. But we can reiterate things and then continue to receive values out from the stream until they are done. Here's that unit lifecycle I mentioned earlier. I forgot I had this slide. Which handles initialization, starting, and processing all the elements. So any of your p-transforms, whether it is a pardo, or a CoGroupByKey, or a combine, or a splittable DoFn, what have you, all of that just falls into this abstraction. And of course, now for the actual meat, how do we actually execute arbitrary functions? Since we don't have named types or overloaded functions or anything similar like the way Python or Java would work, we just end up using reflection. Lots of reflection. The Go library has a method on its reflect value type called call, where you pass in a bunch of reflect values and receive a bunch of reflect values in turn, and can execute arbitrary Go functions. We've extrapolated a little bit from this because reflection, as a rule, isn't the speediest mechanism to do everything, and so we went and made it a little bit more general by extracting it out and having our own little call interface that takes in just vanilla Go interfaces, which you can kind of think of as just a plain Java object, and return, again, a list of list of interfaces in return. And we do this so that we can possibly switch between multiple different ways of executing things as faster methods get developed. So, just as an example, this is just a simple type that has a single method. If you're just executing this directly, you would just, create an instance of the type and then call the method. Great. The alternative way of calling it would be indirectly. This is where we take the actual reflected value, extract the method for that instance, get out one of those interfaces, use a feature of Go called type assertion to get that a value of that type, and then we just call that function. Another way, or at least more directly reflective way, would be to do all of that initial stuff again, but then use that call function that I mentioned before, and wrap our types as reflect.values, and pass that in. And finally, we have why we even abstracted things out in the first place. I'm going to go with the code-generated approach, where we have our reflectX function, which will then take in the foo type, and then call its method out. Take that last line with a little bit of a grain of salt. But there's a reason for all of this preamble. When I said I was generating code, I was talking about generating all of this nonsense. Part of this is because with that whole type assertion thing, there's a faster way of getting the types around as opposed to just wrapping everything in reflect.values, and possibly even just avoiding that altogether. We could pass things around as the generic Go interface type as opposed to as reflect.values or other wrappers. And Go spends a lot of time optimizing how those are executed to get the real concrete types out of these interface types. So we can generate a lot of code to get through a lot of this, and this covers anything that's calling actual DoFn methods, or emitters, or even iterators. But again, there has to be a reason for going through all of that headache, because I spent about 3 months writing the code generator to do all of this. When you call things directly, like I showed you before, it's about 2 nanoseconds a call. That's fine. That's just how long it takes. That's probably more the benchmarking overhead than anything else. Indirectly, through the method I showed, calling a method on a struct, and then type asserting it to that, it's about 180 nanoseconds. That's not super great. Quite a bit slower than just calling the function ordinarily. But if you wrap everything in reflect.value the whole time, it's significantly worse. And unfortunately, without doing anything else, this is what the Go SDK does by default. Because unless you're providing all the extra information, we have no choice but to use the reflective ways to handle everything. Which is why we went and generated all that code, because then we can get that down to 45 nanoseconds. Which, all things considered, 45 nanoseconds is for, unless you're processing like ints in a tight stream, for a lot of functions you're probably doing a little bit more work than summing 2 ints together. So this is quite a bit faster. As a bonus, since there is a code generator to look at your code and generate these things for you, we'll also just generate all the type registrations and function registrations I was mentioning earlier, and register all the little helpers and stuff. And this can be invoked with the Go. For those of you who don't know, Go has a fairly robust code generation mechanism, or at least library time is just built into the tooling. You can type the Go generate command, and it will run whatever arbitrary commands are put in as comments in your Go files. So you can run additional toolings, code generators, the Proto compiler, what have you. In this case, this is the sequence of things to actually generate these these type assertion shims for avoiding all that reflection. Of course, so we're towards the end of my talk. This is obviously not like the complete Go SDK. There's a bunch of things that are implemented that I haven't talked about, like how composites and what that scope variable is for, and so on and so forth. But there's a long list of things that the Go SDK doesn't yet have. But you can get. So if anyone's interested in helping me out, we have a laundry list. We just need to do it. Yeah. It is what it is. As I left to my own devices, I'll get there eventually. But if you want it, come help. And I think that's everything. Thanks.